We're going to start with the cases here. See the first question, what does it say? During an electrolysis of uh, concentrated H2SO4 per disulfuric acid and one and O2 form in equimolar amount, the amount of H2 that will form simultaneously is how much? Okay, see, we have two reactions happening at anode here. At anode, one reaction is um, SO4 2 minus is converting into S2O8 2 minus plus 2 electrons. And this, if you keep it in aqueous solution, acidic form, that will convert into H2S2O8. H2S2O8. Okay. So that is what he's showing, that there is a conversion of this one. And another reaction that would happen is H2O is getting oxidized to O2, which brings it 4H plus, which brings it 4H plus. Now here, while making, while reacting this with water, if you have noticed here, so we would get 2H plus as well. Okay, here. So now O2 plus 4H plus 4 electrons is what it forms, right? Here, right. Now notice this one. If it is been said that if you take this one as 2, and then at cathode, what we expect is that we have 2H plus 2 electrons is giving away H2 gas. Now, whatever be the number of the amount of charge that is used here should be same as the amount of charge used for both of them. Why? Because it is being said that both the reactions are happening at anode, and per disulfuric acid and O2, both of them are forming in equimolar amount. They're forming in equimolar amount. Got it? Right. So suppose if you have a charge of, let's say, how much charge it is being used here for 1 mole of H2, 2 Faraday charge has been used. Okay. So if we take 2 Faraday charge, I have to distribute that 2 Faraday charge into X moles of X moles, because if you notice this, for every 2 Faraday charge, we will get 1 mole of H2 S2O8. H2S2O8. Here. So if it is for X into Faraday, X Faraday charge, then how much moles I'll get? I'll get this as H2S2O8 moles of Faradays, right? And similarly, if you notice here, for 1 mole of O2, we require 4 Faraday charge. So 4 Faraday charge will give you 1 mole of O2. So if at all I say some Y moles of Faraday will give you how much? Correct? So here also, if you notice, for 2 Faraday charge, 1 mole of H2 S2O8 is forming. So for X Faraday charge, it will be X by 2 moles, while here it will be Y by 4 moles. Correct? Now what it has been given is that the number of moles formed here, right? Number of moles formed here is same. So that is X by 2 is equal to Y by 4. Right? So which is equal to Y is equal to 2X. And what is being given is the total charge is X Faraday plus Y Faraday, that is equal to 2 Faraday. Isn't it? X Faraday plus Y Faraday is equal to 2 Faraday. So that is X plus Y is also equal to 2. Okay. So Y is equal to 2X. So 3X is equal to 2. So X is equal to 2 by 3. Okay. So X is equal to 2 by 3. So now if you compare that with respect to the H2, which means for every 1 mole, how many moles of for 1 mole, you would see, where is it? Sorry, here. See, for 1 mole of H2, how many moles of O2 is supposed to form here? because the charge that is being used is only Y Faraday. Y Faraday is Y is equal to Y is equal to 2x. So Y is equal to 4 by 3. 4 by 3 Faraday. Correct? So if you take 2 Faraday charge, 1 mole is 1 mole of, 2 Faraday charge, zero point 0.5 moles is supposed to form. Zero point 0.5 moles of this is formed. So 4 by F Faraday will give you how many moles? So 4 by 3 into 1 by 2 divided by 4. So which means 1 by 3 moles. Clear? So which means 1 mole of H2, if it is forming, 1/3 of the mole of O2 will be forming. Or I can say that it will be 3 times the moles of O2, isn't it? So I can say that number of moles of H2 is equal to 3 times the number of moles of O2. These many number of moles will be formed. So which is how much thrice of this one. Clear? So I hope all of you got an idea how to get this kind of questions. Next, see the second one here. First, let us read the question thoroughly. Half of Zn plus 2, right? Lambda of this one is given. Okay. Now, for such kind of cases, uh, right, see, when you write this one, what do we get the lambda value here? So, the solution here. Lambda m infinity of Zn thrice Fe Cn6 whole twice. That would be equal to 3 times lambda Zn 2 plus infinity lambda mzn. So, and next 2 times lambda m of Fe Cn 6 4 minus infinity. Correct? So, this is the equation we know that. Okay. So, now lambda m of Zn, this one, you can see that half of it is given here. So, if at all I multiply that with 2 here, so I have to multiply 2 on both sides so that this half will get cancelled. So, that is equal to 3 times of, right? Half of lambda is given. So, that will be 2 times of 52.8 plus 2 times of uh, uh, 2 times of this is x. That is what we need to find out here. And that will be equal to, first we'll find out the equivalent form of it and then we can find out the rest. So that is equal to this entire thing, which is 922.8. Okay. So this is what has been given to us. So see, what is that we can calculate? Lambda m infinity of Fe Cn6 4 minus will be equal to 922.8 minus 3 times of 2 times of 52.8 divided by 2. Okay. Now this value is coming out to be 303. Okay. This value is coming out to be 303. Got it? Now, if that is the case, you know that equivalent will be equal to lambda m infinity is always equal to valency factor into lambda e. So we need to find out lambda e infinity. That is equal to lambda m infinity by valency factor. Okay. Now, what will be the valency factor for this case here? You can see for 2 moles, the total charge is coming out to be 6, isn't it? So, Zn will give you how much charge here. For 2 moles, it will be giving out 6 amount of charge. Sorry. This is supposed to be 3 minus. 3 minus. 3 minus. Yeah. Okay. Which means the valency factor is the charge that it carries. So, that divided by 3. So 303 divided by 3. So which is 101. Okay. So that should be the answer. So I hope all of you got this. Don't make any mistakes in terms of writing exactly lambda m and lambda e. Okay. So suppose all of you got this. Right. Let us see the next question now. Let's read this question. Half of HGO plus half of H2O liquid plus an electron is giving this one. If E naught is a standard potential for half cell producing this reaction, then the standard potential for the cell producing this reaction to half of this plus half of H2O liquid will be how much? Ki is the ionic product of water. Okay. So for the first case, if you notice, what we could write as E value here, okay, because he's talking about the cell potential, I could write E is equal to E naught minus 0.0591 by 1 log of concentration term. Can you see this? This is liquid, this is liquid, this is solid. These are all pure forms. So only thing that will be left will be OH minus. This is what you will have it for the first equation. For the first equation, if you write the electrode potential, this is the equation which you will have. Okay. Now, what we need to do is that we need to convert this into such a form where the E naught value cell producing for half of H plus is giving this value. So I need to write it the same same thing for H plus value. Okay. And Ki is given as the ionic product here. Got it? So what I would do, see, to convert into that particular form, I'll do one thing. E naught minus 0.0591 log of, I'll keep this OH minus the way it is. I'll just multiply H plus in the numerator and denominator. Okay. By which you will notice this numerator will become Kw, or in this case it is given as Ki. So E naught minus 0.0591 log of K naught I divided by H plus concentration. K naught I into H plus concentration. Okay. So that will be equal to, right? So that will be equal to E naught minus 0.0591 into log of K naught I, okay, and minus of 0.0591 into log of 1 by H plus concentration. Okay. So if at all, write it this way, sorry, plus. Okay. So plus of, because this value plus 1 by H plus, that would be, if at all I just open it up, so this is what I'll get. Okay. So if that is the case, now what I can write, E naught plus E naught minus uh, E naught minus 0.0591 into log of Ki, correct? In fact, I can remove this part of it. I'll remove this part as 0.0591 into log of K separated plus E naught minus 0.0591 log of 1 by H plus minus log of 1 by H plus. Have you noticed for this equation? Sorry. Yeah. Now, if you notice this equation, what have we got this here? E naught minus uh, E naught plus. So E naught plus 0.0591 into log of 1 by H plus concentration. If you notice this, so I would get this as basically this minus has been multiplied inside here like this. So minus of this entire thing and minus of this entire thing. So it is actually minus of this. Okay. And here also you can write it as minus of this. Okay. Now notice this carefully. What is this value now? This is the E naught value for this equation because this is liquid, HGO, and only H plus is present. So this is exactly what you will have to get this, isn't it? So therefore, now this will be the Nernst equation. Hence the standard potential for this one, because he asked about the standard reduction potential. What will be the standard reduction potential? That will be equal to E naught minus 0.0591 log of Ki. This entire thing should be the standard reduction potential minus 0.591 by 1 into log of 1 by H plus concentration. Okay. So now you could notice that this entire thing is a standard reduction potential or a constant value. That minus this will give you E naught, E of electrode potential. So the question asked is for this one. So what is this value? He is asked. Then, so what is this one now? This is 0.0591 is nothing but RT by F. Okay. So E naught minus RT by F into log of K, which is this one, B. So I hope all of you got that. If anybody has any issue with that question, please let me know. Yeah. Right. Let us discuss the next one. To measure a resistance offered by the solution, which are the following facts we need to consider. Okay. See, first, we learned one thing yesterday. Also, we learned that an alternative current is important for measuring resistance. A direct current is not used. We will be using a Wheatstone bridge, which is correct. See, how is a Wheatstone bridge used? Okay, I didn't discuss anything formally, but I'm sure you guys are aware of this one. Okay, typically a Wheatstone bridge works like this. Okay, so if we have this way, this is how it will be, correct? If you have R1, R2, R3, and R4, so typically Wheatstone bridge will be R1 by R4 is equal to R2 by R3, correct? Usually what we do is that we take here something which is unknown. Okay. So these three are known resistance and one will be unknown resistance. Yeah. So if you want to check out how much is the resistance of the solution which it is being giving, we usually use this Wheatstone bridge and try to calculate the unknown part, given the other three resistance are known. So yes, this is the best technique to understand or identify the resistance here. Got it? R1 by, sorry, R3. R1 by R3, R1 by R3 and R2 by R4. Yeah. Okay. Next, a conductivity cell of known cell constant is used. Yes. See, we need to check out a conductivity cell. Suppose if this R4 is a conductivity cell, we need to know what is its cell constant values. How do we get cell constant value? G star. So we will take the dimensions as L by A. L being the length in that conductometric cell here, like this, right? This way. This is the distance L, and area is the area of the cross section of the electrodes. Right? So yes, this one is also a fact. So to find out the resistance, these three are the parameters which we need to take care of. Next. Check out next question here. First one. Molar conductance gives the conducting power of all the ions provided by 1 mole of a substance. That is true. The whole idea is we require 1 mole of an electrolyte, right? And that will give us the power. Right. Next, molar conductivity of NH4 plus and NH2 minus in ammonia medium are equal. Okay. Well, they are not, because the size of the ions could be different. Okay. Because molar conductivity also depends upon ionic mobility of the ions. Correct. So a positively charged ion and a negatively charged ion may not have the same amount of molar conductivity. You can check this in reference to H plus and OH minus. H plus has around 350, while OH minus has around 200 molar conductivity. So you can see, although they both come from same water molecule, they might have, I mean, on dissociation of water molecule, you'll get these two ions. Same way, dissociation of ammonia, you'll get these two ions. But it is not necessary that they have to have equal amount. This is incorrect. Molar conductivity of ions increases with increasing temperature of the solution, which is true. Okay. Because on increasing temperature, the mobility of the ions increases, and molar conductivity is directly proportional to mobility, ionic mobility. Molar conductivity of ions decreases with increase in the pressure of the solution. That is true, because more amount of pressure is being applied, correct? Less will be the mobility of ions. Correct? So that's why uh, you notice that the molar conductivity will decrease. Next. See the next question here, sixth one. In conductometric titrations, it is possible to locate end point and not equivalence point. That is true. Okay. Okay, so what is this equivalence point and end point? If you have, if you remember, I I'm on while we were plotting, I always wrote this as dotted lines like this. Okay, so if you notice this one, this is the end point. That means practically you figure out how much it is, isn't it? Okay, so where exactly to stop? Okay, so where the minimum amount of reading comes, and then it will start increasing again, that is your endpoint. Got it? And identifying exactly equivalence point is not possible because it will be somewhere close to it. Because exactly this might not be the value, this might not be the exact value of it, volume of it. So the volume might be slightly lesser than that. So usually equivalence point will always be equal to V plus or minus delta V. And delta V is small value, but it will be somewhere close. Okay. But what we can see is the end point where the minima is reached for a molar conductance versus, right, when it will again start increasing. Sorry. Next, precipitation titration cannot be carried out by conductometric method. Okay, conductometric method. Okay. The reason for that, which is correct here, the reason for that is, you will see for precipitation cases, almost the lambda m remains same. Lambda m remains same. Hardly it will change. What beta? What is the difference between endpoint and equivalence point? Okay. See. Oh, sorry. It is given endpoint and equivalent. Sorry, my mistakes. Ajay, please check this. What I'm trying to say is, it is easy to locate equivalence point and not the endpoint. Equivalence point is theoretical. Beta. Theoretically, we know that M1 V1 is equal to N1 V1 is equal to N2 V2 for an acid and base reaction. Okay. So where the change could happen, that we could figure out. Okay. Based on lambda m value, as the change happens, we could figure out. Clear? So theoretically, we will be able to figure out what exactly is the value V2. This is theoretically we can figure out. So theoretically, what you are trying to figure out is called equivalence point. This is called equivalence point. But practically, you will not be able to identify this exact point. You'll always be finding V plus delta V value. Got it? Ajay, understood? While making titrations, you will see sudden change in the lambda m value. It is like this. Suppose lambda m value reach to, let's say, 100 here, correct? It has reached to 100. After that, after adding some amount, again, this 100 is observed to be the same value, and then it reaches, then it starts increasing. So we are not finding exact point here, right? So, but what we could find out is this range. We can only say that within this range, somewhere there will be V hidden. Okay, volume of the base which is required is hidden. Okay, so which means we can figure out theoretically where is the equivalence point, but practically this point is difficult to identify. So practically, what point you identify is called the end point. Ajay, clear? Right. So yes, in conductometric titration, it is possible to locate. I read it differently. This should have been here. This should have been. Equivalence point can be identified, but not the end point, exact end point. So that's why this is incorrect. Next. Precipitation cannot be carried out in conductometric titration. See, initially, if you notice, it will always have lambda n equal. But you know that suddenly when it raises, that means there must be some change here. So you will notice that again, we can just give some amount within this volume range. We know that within this volume range, we know that there is an end point present. So yes, we can figure out the conductometric using conductometric titrations. So this is also incorrect. Okay. Next, a concentration of the titrant should be relatively more than 10 to 20 times than the solution being titrated to minimize dilution effect. Okay, correct. See, see, if you have it like this, correct. So this is your titrant and this is your titrant here. So when you titrate both of them here, if this value is sufficiently enough, that at least 10 to 20 times is more, then it will help it to identify the exact equivalence point and also minimize the dilution effect. That means here you will not have too much of dilution of the solution. Got it? So if you have too much of dilution of the solution, that affects the lambda m value. Lambda m value, because as the dilution keeps happening, more and more lambda value, I mean the alpha value keeps increasing. Okay. To minimize that effect, we always add more amount of titrant and less amount of titrant. Got it? Next, in titration of the strong base with a weak acid, which is titrant, okay, uh, conductivity increases before the equivalence point and remains almost constant after the equivalence point. Okay, see how is it used here. So if we take the, just a minute. See, if in the titration of strong base with a weak acid, which is titrant, so your titrant is here. So that means the acid is present in the burette, titrant, and then base is present here. Correct? This is strong base and this is weak acid. Okay. Obviously, you are measuring the conduction in this vessel. So, if by chance here, if you notice the conduction is, sorry, when the titration is done, what is happening? OH minus ions are concentration of that is decreasing, Cl minus is increasing. So, what should happen to the initial amount? Initially, the conduction should always decrease. And as it increases, right, after the equivalence point, No matter how much you add, hardly there will be any increase here. Why? Because now you'll be only adding weak acid. So this is how the graph should look like. Okay. So guys, be careful what is being used. Okay. So this is the volume of acid. Earlier, the graph which you used to make is when weak acid is here and strong base is here. Okay. But he is asking the different way here. Correct? If this is the way, then what will be the case? Now notice in the titration of this one, conductivity increases. Is it increasing or decreasing? It is decreasing actually. And then it almost remains constant after the equivalence point. So this is also an incorrect statement. Okay. So A, B, D are the options. Please check once. Anybody has a problem with that or any issue with the question? Let me like see the next one. See. Which of the following is correct in the given options here? O2 is becoming this one. So this is a reduction of O2 value given, and the standard half cell potential of this plus one electron will be this one. Okay. See, if you use the word standard, it doesn't matter whether you divide half or two or anything because it is an intensive property. E naught value does not change. Stoichiometrically, it will not change. Okay. By the way, E cell or E naught cell, both of them are intensive properties. Okay. Second, the standard half cell potential of this will be uh, standard half cell potential of O2 plus H2O plus OH minus will be this much. Standard half cell potential of this one OH2 plus 4 this much. Okay, let us see how we can get this. O2, I have, we have only one equation to support. O2 plus 4H plus 4 electrons is giving 2H2O liquid. For that, E naught value is 1.229. Okay. Now I do require a case where I get 4 electrons here, but this time it is giving 4 OH minus. Okay. What is the other form which I know about water is that water when it is getting reduced, uh, plus 2 electrons giving H2 plus 2 OH minus. For this, we know that E naught value is not value 0.83 minus. And we also know that 2H plus 2 electrons will give you H2 gas that E naught value 0. These are the known reactions which we know that. We just need to use this and try to figure out how we can get the overall reaction which is given in the question, which is O2 plus 2 H2O liquid plus 4 electrons is giving 4 OH minus. Okay. Well, you see, we have to use these three equations to get this one. Okay, that's the only way we can do it because these are the only known equations we have. So let's see what we could do here. Let us put this as delta G naught 1, delta G naught 2, and delta G naught 3. Okay, and this is delta G naught 4. Well, to get this equation here, correct? So first I need to definitely add delta G naught 1, and then I have to multiply this with 2 here. I have to multiply this with 2 here, right? And then multiply here also with 2, because I require 4H plus. Yeah, here also I need to multiply 2 here. But I need to subtract this. So what do I get here? Delta G naught 4 is equal to delta G naught 1 minus, not minus, sorry, plus only, plus delta G naught 2 into 2 minus del 2 times of delta G naught 3 into 2. That will give you delta H naught 4, correct? So now let us put that in terms of values here. So 4 times of, what do we have? 4 times of uh, 4 Faraday into E naught of 4 is equal to, this is also equal to 4 times of Faraday into E naught of 1 plus uh, 2 times of Faraday into E naught of 2 into 2 minus 0. Okay. E naught cell for this is 0. So therefore, now what do we have here? So E naught 4 is equal to 4 E naught 1 plus 2 plus 4, another 4 E naught 2 divided by uh, 4. Yeah. So 4 will get cancelled. So we basically we'll have E naught 1 plus E naught 2. That's it. That is what we need to do. So how much we have? Let me check. 1.229 minus 0.83. Okay. So we are getting this as 0.4. Okay. And yeah, I think that is what he's asked. So B is correct. Please check. I hope all of you got this point. Next. C. If O2 at 1 atm is passed through water, the cell potential for this would be 0.816. Pass through water, cell potential for this is the same equation used. First plus 4 plus 2H2. Well, you see, O2, if it is passed through water, the cell potential, which is this one, is saying that now it will change to 0.816 volts. Is it correct or not? That is what has been asked. Okay. See, when you have it as an anode here, you have as an anode here, and usually we notice that we'll have the dilute H plus solution here. So dilute H plus solution. So major content is water only. So it is which is being water which is being oxidized in the form of O2 plus 4H plus uh, plus 2 electrons, isn't it? Sorry, plus 4 electrons. This is what is the oxidation happening. This is the oxidation happening. Now, he is asking exactly the reverse process. What if I push the O2 here What if I push the O2 here at constant uh, value here? So in that case, what would I get? I need to check out, because it is a pure water, H plus concentration will be 10 raised to power of minus 7. So therefore, if you check out the E value here, E value will be E naught value minus 0.0591 by 4 log of H plus concentration raised to power of 4 into pressure of O2 given is 1. So now you just need to multiply this and check. E naught value is given as 1.229 minus 0.06 by 4, and this 4 can come out here. So log of H plus concentration, and that is equal to 1.229 minus 0.064 will get cancelled, and this will become minus 7, because H plus concentration is 10 raised to power of minus 7. So that makes it 1.229 minus 0.42, right? 0.42. So that will be plus, I guess, 10 raised to power of this one. O2 plus 4H plus will be this one. Oh, I have written it the reverse form of it, so minus of it. So this has to be minus, because I have written the equation in a reverse manner, so it should be minus. So it should be 1.229 minus 0.42. So that is coming out to be minus 0.81. Right. That is coming out to be correct. So if you reverse this again, this minus will become plus. So this value is correct. Okay. So I hope all of you got this. In pure water, or I would say as mild acidic water, this is the equation which you will have. I need to find out the reverse of it. First, I calculated what is the E value for that one and reverse that value. Reverse that value, you will get this. So that is correct. If photo is passed through water, the cell potential. No, this is incorrect, because this one is coming out to be correct value. Very good question, everyone. Please check this out. Seventh one was a very good question. Very simple concept. Just the uh, just the electrolysis of water, and you can see how good the question can be. Done. Next. First, we'll come to these questions, and we'll finish off these hard questions. Then we can come to mains questions. Okay. These are typical advanced questions. So let us see. The next question. Yeah. First, AgCl. I'll just give you the hint of this one. See, E naught value is given for this one. E naught value is given for this particular equation here, and delta G naught value is given. Delta G naught value for these two are given, and E naught value of this sparingly soluble salt is given. We need to find out delta G naught formation of Ag and plus. Okay. What we need to find is what, let us understand that. So what we need to find is Ag plus delta G naught formation of this one over here. The formation part is present here. So I need to find out this value. For that, what all things we know. Delta G naught value of ammonia is given, and AgCl, Cl minus we need to know. Okay. AgCl formation is given, Cl minus formation is given, and overall E naught value is given. So I think from the first part, it is pretty much clear how we can get it. See, first, we need to use the first equation to get the first option here. See, I require this value. and overall delta G naught of the reaction, let me write down, delta G naught of the reaction will be equal to delta G naught formation of Ag NH3 twice plus, correct, plus delta G naught formation of Cl minus, and that minus delta G naught formation of AgCl, and that, sorry, and that minus 2 times of delta G naught formation of ammonia. Okay, so these are the forms which we know, correct? Delta G naught formation of ammonia, 2 times of that. Okay, so let us put what all things that have been given here. Since the E naught value is given to us, I can write delta G naught value as minus NF E naught, uh, E naught value, which is equal to, this is X, that's what we need to find, plus C naught, CL value is given as minus 131.23, and minus of AgCl formation will become plus 109.79, and minus 2 times of ammonia form. I think the ammonia form, right, we can find out from these two here, these two information. Uh, Let me put this as Y for now. I'll show you how we can find out. Okay? Like this, Y for now. Uh, for this, what we can say, yeah, we got one equation here. Everything else is known for it. So what about number of moles here? See, silver is, if you notice here, there is no oxidation or reduction that is taking place here. Right. So ammonia is just getting formed into this particular complex. AgCl is this much. What values given? Hmm. See, whenever there is a complexation formation here, this is all coming from AgCl only, right? AgCl will have only one electron transfer. So we can always take this N as one electron, correct? E naught value is given, Faraday's is given. So you can get one equation of X and Y. Okay. Next, AgCl plus NH4OH is giving this value here. Using these two, I can find out what is for ammonia. Okay. So you can notice that. Uh, if we subtract these two, so what would I get? On subtraction, we'll get this as 2 moles of NH3, correct? 2 moles of NH3 plus 2 moles of H2O will give us 2 moles of NH4OH. 2 moles of NH4OH, okay? So delta G naught value for that will be equal to, let us, delta G naught 1. I'm putting this as delta G naught 1 and this as delta G naught 2. So that is equal to delta G naught 1 minus delta G naught 2. Okay. So number of moles are constant here. N value is constant here. So we can write this as, uh, for this particular equation, we can write delta G naught value is equal to minus F into minus of minus 0.151 minus of F into minus F minus of 0.359. Okay. So that will be equal to F will come common here. So minus minus will become plus, minus minus will become plus here. So 0.151 minus 0.359. Okay. So this will be the value of delta H of the reaction. And if I know delta H of the reaction, I know this value, I know this value. Now I can find out what is the value of ammonia. So therefore, delta G naught formation of 2 times of delta NH4OH minus 2 times of delta G naught NH3 minus 2 times of delta G naught H2O, that will be equal to this value. So F into how much we are getting? 0.151 minus 0.359. So that is minus 0.208. Okay. So if you do this, because now this value is known, I know this value is known, we can calculate what is ammonia form. Now, once I get to know the delta G of ammonia, substitute that value here, I'll get to know what is the value of X. We'll get to know what is the value of X also here. Okay. So I guess this part is clear. Right. So I have calculated this. I'm getting exactly these two values, A and B. Okay. Next, the standard potential reaction for this value AgNH3 plus H2O giving one electron, taking one electron to give silver precipitation with NH4OH is this much. Okay. Now for that, what are the equations we need to use is this one, and we need to use this one. So again, delta G naught minus delta G naught 1 minus delta G naught 2. So if we do that, and there is one more equation which I need to use is this one. Okay. Oh, here it is given wrong. Here it is silver. Okay. Solid. So E naught silver is given. Three equations I need to use. So equation 1, equation 2, equation 3. So if you add these three equations properly, you will get this equation. Got it? And that value is coming out to be exactly 0.581. So when you take it, so this is also coming correct. Okay. And last one, this is not exactly coming out to be 0.2. Okay. So I hope all of you got an idea here how to do this question. Right. From second, we can get directly. For which one? Option A, B. Which one, Ajay? A. AgCl is given, but we don't know the value of this one, na beta? Ajay? These two are unknowns. Ammonia was also unknown. This is also unknown. Both were not given. That's why we require two equations. This equation as well as this equation. Got it? Are you talking about option C? How to find out? Fine. Let's go ahead. Now, let us see the next question here. We'll run through a little fast with the questions here now. Let's see. This is one standard type. Okay. What I'll do, uh, let us skip this one. These three are similar ones. Uh, let's see this one, 12th one. This is because this is one very standard type of question that will be asked. So we need to learn this. Check. E naught value for Ag plus 2 Ag is given. E naught value of this particular um, sparingly soluble salt is given. Then the standard equilibrium constant for this is how much? Okay. Again, a very standard question. So let us write the equations which we know. Ag, Cn twice minus plus an electron will give us Ag plus 2Cn minus. For that, the E naught value is given as minus 0.38 volts. Okay. Next, another thing which is given is Ag plus an electron is giving Ag. For that, the E naught value is given as minus 0.8 volts. Okay. So, in case if at all we'll try to add these two, so what would I get here? to this, no, subtract this, then we can get that problem. So we can take this as equation 1 and equation 2. Okay. So this value is plus. Next. So if you subtract this, what do I get? AgCN twice minus. Okay. That is giving Ag plus 2Cn minus. This is what I'll have. And E naught value will be minus 1.18 volts, because this minus of this will give you minus 1.18 volts. The delta G naught value is minus NF E naught cell, and that is given as minus RT ln K equilibrium. So from here, this will be equal to minus 2.303 RT into log of K equilibrium. Okay. So from there, I can find log of K equilibrium is equal to NF E naught cell by RT. You know that value comes out to be 0. Uh, E naught cell value we found it as 1.18, and N value is 1 divided by this value comes out to be 0.0591, correct? So that is coming out to be approximately 0.06118. So yeah, around minus 20. So K equilibrium is equal to 1 into 10 raised to the power of minus 20. Okay. So X value is 20. Correct. Next. Check out this 13th question. P equivalent weight of H2SO4 in the following reaction is a very, very important question. Normally, whenever we think about H2SO4, one thing we get in our mind is that this is a acid, strong acid, which can produce two H plus and SO4 2 minus. So therefore, valency factor should be 2. Okay. As a general acid, it is true, but when it is present in what do you say, cell here, okay, lead storage cell. In the lead storage cell, if you notice properly, what is happening is lead will be reacted with SO4 2 minus to get this as PbSO4 plus 2 electrons. This is what is happening at anode. And then PbO2 plus SO4 2 minus plus 4H plus 2H plus 2H um, 2H plus 2 electrons. Okay, correct. So 4H plus minus 4H plus. So that is giving out to be again PbSO4 plus uh, PbSO4 plus H2. Got it? To H2. So now problem here is, if you notice the total number of, as the balanced equation here, PbO2 plus Pb, this together I can write it as 2 moles of H2SO4, isn't it? 2 moles of H2SO4. Plus, this is the 2 electrons which are giving and taking up to get 2 moles of PbSO4 plus 2 moles of H2. Okay. So what have we learned, that we are using 2 moles of H2SO4 to drive 2 electrons, which means what should be the valency factor now? So valency factor for H2SO4 now should be 1, not 2. Okay. So the valency factor is only 1. Clear? So this is an important part, because for 2 electrons, we require 2 moles of H2SO4 for the reaction to happen. So therefore, valency factor is 1, and equivalent weight, if it is asked, equivalent weight of H2SO4 in lead storage battery is 98. Please remember the lead storage anode and cathode reactions as well, everybody. Yeah. Next. Check out another standard question here. Hg2Cl2 plus 2Ag giving 2Hg plus 2AgCl. Temperature quotient is given. Find the delta S naught value. Okay. So remember the formula directly. Delta S naught is equal to NF into dou E cell by dou T at constant pressure. Okay. So here Number of electrons transferred from here to here is 2 electrons. Here to here is also 2 electrons. So therefore I can say 2 times into 96500 into 0.02. Okay, clear? And this entire thing I require to put it in kilojoules, so divide it by another 1000. So that's it. So you will get the value as I think 3.8 or something. Got it? Next. Notice this question now. See, next one. The EMF of the cell formed by dipping two electrodes in metal in two solutions of its salt, in which the concentration of the metal ion is given, the zero point 0.1 and zero point this one was observed to be 0.3 volts at 25 degrees. What is the valency of the metal ion if two half cells are connected using a salt bridge? Okay. So we need to figure out what is the value of N here. Okay. So two electrodes of metal. So one metal is converting into Mn plus, right? This is a concentration cell. So this is an anode form plus N electrons. The value given is 0.1 and Mn plus N electrons giving M. This is cathode. So here the concentration given is 0.001. So what will be the Q value? Q value will be equal to 0.1 by 0.001. So just write down what is the E value. So E is given as 0.03. E naught value will be 0 minus 0.0591 by N, which we need to find log of 0.1 by 0.001. Okay. So if I take this as approximately 0.06 by N, and log of this is coming out to be 10 raised to power of 2 here. So then N value, if you calculate, it is coming out to be 4. Okay, done with it, everybody. Next, see this question. NO3 minus giving NO2 in acidic medium. E naught value is given. NO3 minus is giving NH3OH plus in acidic medium. What will be the pH of the above two solutions if they have the same E value? Okay, so always write for both the equations separately. So first for NO3 minus in acidic medium. So which means I should have something like 2H plus NO3 minus to give this as NO2. Sorry, it should be taking one electron because there is a reduction. So plus one electron to give NO2 plus H2. Isn't it? For that the E naught value is given as 0.79. Second equation, if you notice, NO3 minus, right? This in acidic medium giving NH3OH plus. Okay, so you have to balance it first. Plus NH3 NH3OH plus NH3OH plus. Now notice it here the oxidation state here is plus 5. Oxidation state here is plus 5. Here if you notice x minus x plus 4 minus 2 overall equal to plus 1. Okay, so that is equal to 2, 2, 2, 2. So 2, so 2, so minus 1. Okay, this is coming out to be minus 1. So nitrogen is at minus 1 oxidation state. So how many electrons are transferred from here to here? 6 electrons. See, same acid may be of different concentrations. Same in acidic medium, here also in acidic medium, but of different concentrations. In the first case, only one electron transferred. In the second case, 6 electrons are transferred. So NO3 minus plus 6 electrons plus 6H plus, that will give us NH3OH plus H2. Okay. So now, what will be in the first case? Let me take some gap here. In the first case, I can write E naught value, E1 value as 0.79 minus 0.0591 divided by n. N is 1 log of, okay, 1 by h plus square concentration. This is from first equation, which I can write it in terms of 0.79 minus 0.06. And that minus, if at all I take it inside, sorry, that minus, if at all I keep it like that, this will become simply 2 times of into 2 times of minus log of H plus, and minus log of H plus is what? pH. Okay. So this will be the first equation. See for the second equation. The second equation, E2 will be equal to, how much is the value here? 0.731. 731 minus 0.06 divided by 6 log of 1 by H plus whole raised to power of 6. Okay. H plus whole raised to power of 6 here. Isn't it? It's balanced. 2 oxygens, right? Sorry, there's only 1 oxygen. I don't think it is balanced. Oh, this should be 8 beta, 8 H plus. So 10 H plus raised to power of 8. Yeah? So now you notice that E2 is equal to 0.731 minus 0.01 into 8, correct? And that minus, if at all we carry, it will be minus log of H plus concentration, which is equal to pH. So 0.731 minus 0.01 into 8 pH. Okay. So we got the pH. You just have to equate both of them. So this value equal to this value. That is what the question said. So 0.79 minus 0.06, 0.06 into 2. That makes it 1.2 of pH is equal to 0.731 minus 0.01 into 8 times of pH. So if you put both the pH on one side, it is coming out to be 1.5. It's a good question. Please check this. Okay. So I hope all of you got the idea how to do this question. And everybody.